So, hello everyone, hope you're doing good and welcome back to my channel. Today is day 30 of the Upper Daily Letcode Challenge. Today is the last day for the Upper Daily Letcode Challenge, and it is a hard question for us. It's question 1579. Remove maximum number of edges to keep graph fully traversable. To keep graph fully traversable. Okay. So now let us quickly understand what the question is. First, let me show you what are the inputs given to us. We are given an input n and we're given some edges. Each of the edge has three integers. What are they? I will just tell you now. So just understand this input. Okay. So now what they're saying is we are given an undirected graph of n edges. So what is n? N is the number of nodes, okay? And there are three types of edges present here, okay? The types of edges are three. What are they? See, type or inference. The one, see, I will just show you this diagram. See, this is going to be the diagram given to us, okay? Yeah, this is the one. So there will be three types of edges. You can see there are three colors being used for the edges. So we have three types of edges. So what are they? See, type one can be the edge which can be traversed only by Alice. Okay, Alice is one person who can travel only on the edges of type one. Okay. Similarly, there is a person Bob who can traverse only on the edges of type two. Okay, and there is something called type three which can be utilized by both Alice and Bob. So what are they? Type one can be utilized only by Alice. Type two can be used only by Bob, and type three can be used by both of them. So if you see this example, see the blue one is the type 3. That means both of them can use it. Red one is can be only used by Alice, and similarly green one can only be used by Bob. Okay, so that is the basic idea of what they have mentioned here. Now let us come to the second input, that is the edges. What are they? Let us see. See, we are given edges array, and each edge has three integers. Okay, what are they? First integer represents the type of the edge. Okay, whether it is type 1, type 2, or type 3. Okay, and the other two integers represents the source and the target of that edge. Okay, for example, if we are having like this, that means there is edge between 1 and 3. Okay, this is 1 and 3 of type 1, of type 1. See, of type 1 means this red color, you can see here this red color. Okay, similarly, if we see this, there is an edge of type 3. See, here 3 is mentioned, that means there is an edge of type 3 between 1 and 2. Between 1 and 2 of edge of type 3. Type 3 is blue. So you can see there is a blue edge between 1 and 2. Okay. If you can see my mouse pointer, this is I am showing here. So that is what they have meant here. Okay. So they are talking about a bidirectional edge here of type 1, type of I between nodes GI and VI. Okay. So what see now the starts the question. Okay, now the question starts. Find the maximum number of edges you can remove so that after removing the edges, the graph can be fully traversed by both Alice and Bob. So at the starting itself, let me tell you, see, there are two characters, say Alice and Bob. We have to treat them differently, okay? So what they're asking is we have to remove some edges of any of these types. Okay. See, this thing you may not be able to understand in their beginner. See, if you are beginner, see this thing is not mentioned. Okay, any one of the any edge can be removed which can be of either of the types, but after removing it we have to see the edge should be traversable, okay, such that we have to remove the maximum edges possible such that still the edge is traversable by both Alice and Bob. See, when we say both Alice and Bob, we mean see Alice can follow only certain path. Okay, it can follow only type one and type three paths. Similarly, Bob can follow only type two and type three paths. So we have to remove as much edge as possible of any of these types. Okay, of any of these types, such that after removing them also the edge remains, the graph remains traversable for both of them. Traversable means they should be able to reach all the end nodes. Okay, that is the meaning of traversable. If we read this part, this is what I mentioned. Okay, can you so that after removing the edges, since the graph is traversed by both Alice and Bob, the graph is fully traversed by Alice and Bob. If starting from any node, they can reach all the nodes. Okay, so we have to remove the maximum number of edges as much as possible of any of these types. See, of any of these types, this word please highlight it. This is not mentioned in the question. You will not be able to understand it in the example. But only if you try and write a code, you will fail that exercise. Only then you will understand that. See, normally people will think that they can have to remove only these two types of edges. Okay, they will think the type 3 edges which not need not be removed. But in this question, they have meant all other type of edges. Okay, we have to find all, see whatever edges possible, try to remove it. If the graph can still be traversed by both Alice and Bob, then it is counted. Okay, then it's counted. Okay, the graph is fully okay, fine. Then the maximum of edges that can be removed, and return minus one if Alice and Bob cannot fully traverse the graph. Remember one point here: we are not adding any edge here. We are only removing the edges. Okay, so if a graph is given to us where the starting itself it's not traversable, then we have to return minus one. Okay, fine. Let me quickly trace the examples for you. It's example one is very important. Let's see. It's like a big example. Let me quickly tell you. Okay. So from the graph coloring, you will be able to understand that red represents the type 1, that means Alice can travel, green represents the one which Bob will travel, and type 3 is the one which anyone can travel. So these are the edges. Please look at, pause the video and have a look at it. Now they are asking which others can be removed. Okay. So let me start from one and let me talk about Alice first. Okay. So see, I can travel only red and blue. Okay. I can travel only red and blue. So see, consider that blue is already there. Okay. So what are the connected ones? 1, 2, and 3 are connected. Okay. I need to connect only 4. Okay. So which edge do I need? Okay, 2 to 4 edge I need. Okay, this red edge I need. But see, now all are connected. So this 1 to 2 red edge and 1 to 3 red edge. These two are not needed. Okay, 1 to 2 red edge and 1 to 3 red edge. Red edge means type 1 edge are not needed. Okay, it can be removed. Now come to Bob. Again, I will see. Again, consider type 3 edges are already there. So 1, 2, and 3 are connected. I am Bob, so I will need a green edge. Okay, so you can see green edge connects 3 and 4. So there's no edge which I can remove for Bob. Okay, so for Bob, no green edge will be removed because that is a bare minimum we need to traverse. Okay, so only the red edges will be removed, and which are the ones connecting 1 and 2 and 1 and 3 connecting red edges. Okay, so you can see the ones connecting 1 and 2 and 1 and 3, and it's of type 1 because I am saying it's red edge. Okay, so only two edges that can be removed. Now come to this example. See, again the blue edge connects 1, 2, and 3. That is fine. Okay, there is a bare minimum. Now we have to connect 4 somehow. Okay, so you can clearly see green for Alice is this is the only edge. There's no edge which we can remove for Alice. Similarly for Bob, this is the sorry, I'm taking the reverse. This red is for Alice. So we cannot remove it because there's the only edge which connects 4. And similarly for Bob, this green has the only one which connects it from 4. Okay, so nothing can remove that. But see, one thing, they are traversable. Okay, they can still reach all the nodes. So the answer is 0 and not -1. Okay, now this example is very important because you are getting -1 here, right? This example is an edge case. We will find this in the coding also, so please pay attention here. Now see, all first let me see if they are even traversable for the given graph without doing any edge also. See, so I'm starting from here 1 to 2, 2 to 3. I'm talking about type 1. That means I'm talking about Alice. But see, for coming from 3 to 4, I need see Alice cannot travel, right? Alice cannot travel on green edge. Only Bob can travel on green edge. Okay, so Alice cannot travel to node 4. Similarly, if you talk about Bob, Bob cannot travel to node 1 because node 1 can only be traveled through red edge, which means only Alice can travel. Okay, so both Alice and Bob are not able to reach one of the nodes. That means this graph is not fully traversable in the starting itself without removing any nodes, any edges. So this we have written -1 here. Okay, the graph is not fully traversable. It is impossible to travel the graph fully. Okay, so this was all. And if you see the constraints for n, it's very high. Okay, you will have to think about optimized solution. So let me tell you very briefly. There is a disjoint union set data structure which we are going to use here. See, union means what? See, whenever you are hearing this verse, please try to understand the basics of it. What is a union? Union means a group. Okay, a group. And connected. See, nodes which are connected is called a union. Okay. We'll quickly let us see what it is. The disjoint set union. Okay, please remember this word, disjoint set union. In short, we'll call it DSU. This is going to be a data structure which we are going to use here. Okay, in graphs, if you have seen the Leetcode graph card, so this is also going to be a very important, you know, data structure, or is actually algorithm, but Leetcode refers to the data structure, right? So it's going to be important algorithm. There are many questions which can be solved through it, and if you have been following this April Daily Code Challenge, the last 3 days we have been getting questions for this data structure. Okay, so what they are, see, let me quickly give you the basics, then we'll go for the coding. Okay, it's a hard question. It will take time for you to understand, but please do spend that time. It's a very nice question to begin with. Like, but very frankly, if you are a beginner, if you are thinking it's not possible to understand this, you are wrong. You should spend time, and definitely you will feel benefited. If you are able to spend the time, you will definitely feel benefited. Okay. So what is it? See, the disjoint set union can detect if two nodes are connected with some path or not. Okay? So see, union means what? See, if 2 and 4 are in a union, that means they are connected. Okay. If two nodes I find, if I came to know that they are in the same union, that means they are connected. That is the basic idea. See, what we'll do is for every edge, if two nodes were not connected earlier, we know this if SH is required. Okay, see, if see I have a union A, I have a union B. Now comes the edge. Okay, I will check. See, edge means there will be edge between U and V. So let's suppose if U and V are in a different unions, that means this edge is must. If U and V are not in different unions, that see, when I explain the code, it will become more clear for you. But for now, just understand. See, there are two unions. Okay, there are two unions. See, for example, this is a edge between U and V. Okay, I will just check if the union in which U belongs and the union in which V belongs. If they are same, that means they are already connected. I do not require the current edge between them, so I can remove that edge, right? But if they're not connected, that means the edge is very much required. It cannot be removed. That is the basic idea. For every edge, if the two nodes were not connected earlier, we know this edge is required. That is the basic idea. We use DSS to perform the unions of two nodes. Okay, that is what I told you for an edge. So whenever edge comes between U and V, we'll try to check if U and V are in the same union or not. Okay, and if the nodes were not connected earlier, that is, if they have see, every union will have a representative. Okay, just imagine. See, these things if I get to that, it will be better for you to understand. But see, just imagine, for example, there's a group. Let us say 1, 2, and 3 forms a group. There will be a representative for the group. Let us say node 1 is a representative for the group which contains 1, 2, and 3. Okay. So that's the basic idea. So what I'm saying is, see, if the nodes were not connected, that is, if they have a different representative, then we will know this edge is needed. Okay. I've already explained you that whenever the edge between U and V, will check if the union which U belongs and the union which V belongs, if they are the same, then we do not need that edge. If they are not the same, then we need that edge, okay, which cannot be removed. To get the answer, we can subtract the number of required edges from the total number of edges. As I told you, how I will find the required edge, I will explain that in code as well. So from this, we'll get which are the edges which are required, and this we will subtract from the total number of edges to get the number of edges which can be removed. Okay. To check if the individual graphs are connected, we'll see if the number of components in the graph is 1 or not. Okay. See, one more thing, as I told you, see, this as I said, this is a very important example. See, whatever be the question, but if the starting itself the graph is not connected for Alice, see, Alice consider a separate graph or Bob consider a separate graph. If any one of them are not connected at the starting itself, then we have to return -1. That is what is being talking we are talking about here. To check if the individual graphs are connected, we'll check if the number of components in the graph that seem whenever we form a union now. See, I think when I explain the code that time you will understand it better. Okay, let me come to the coding part. See, this last point I will explain after explaining the code. Okay. This is see, yeah, from here to here is going to be the data structure which we are going to use. Okay, this is called a union find data structure. Our real answer starts from this class. Okay, let me quickly explain you what we are doing. Each component. Okay, initially each node will have its own representatives. Okay, so totally you might have understood by now there will be n representatives. Okay, so this parent is what is called we are calling the representative. So parent is representative for a node. Okay. So suppose there are n nodes, there each of them initially will be representative of their own. So there will total n parents. Okay. Whenever I see parent, it's not a parent or a see parent means representative here, not a node edge connected to it. Okay. Parent means representative. Okay. Just thinking there's no connection between a parent and child here. Okay. Just think a parent is just a representative of a node. Initially the parent. So that means every node will have the same representative initially. Okay. Every node will be its own representative initially. Next comes the size data structure. Size means for each representative, it will show how many, like see, for example, node 1 is a representative for a union which has 3 nodes. So the size for the node 1 will be 3. That is the basic idea. Okay. It stores the number of nodes in the component with node as a root node. Okay. Initially, the size of the component is set to 1. So you might have guessed it correctly. So this is also array of n nodes. Okay. See, I am giving n plus 1 for safety here. See, for example, in this case, there's no 0 here. You can see, right? 1, 2, 3, 4, there's no 0 here. So to ensure we have n nodes, that means from 1 to n nodes. So for that, we'll require n plus 1 in see, because index starts from 0, right? That's why I'm giving n plus 1. But when I'm explaining, I will be saying n only, right? That is the idea. See, we'll come to these things again later. See, actually, the question starts from here, okay? This is just a data structure here, right? So then this is the component. Okay, what is the component? Stores the number of components in the graph. Initially, it will be see. Initially, each node will be considered as a separate component. Then we'll be unioning them. Okay, that means two components will be merged. Whenever so for example, node has a graph has 5 nodes, we will be merging some of the nodes. Okay, initially, if all the after everything, if all the nodes are merged, that means we will have only one component instead of 5. So that is the component here. Okay, initially it will have 5 components, but after merging everything, based on if they're connected or not, we should have only one component. See, that is the basic idea here, and that is what is actually we are talking here. But I will come to this later. Okay. Yeah. So suppose the number of components in the graph initially it will be equal to 1 because each component will consider separately. Each node is considered a separate component initially. Yes, yeah, that's the basic idea. Now come to the first I will explain the union data structure. Then we will go to the union function. Then we'll go to the find function. Okay. What we are doing is see find function will give me the representative for x. For example, I have a group which contains 1, 2, and 5, and the representative is 1. Okay. For when I say find a 1, it will give me the representative of the union to which x belongs. Okay. What find gives? It returns the root node for the parent hierarchy. That means the group which x belongs to, its representative node. Okay. So uh, self dot find of x, I will call it as x. Self dot find of y, I will call it as y. Okay. X and y I am getting from here. I'm doing a union of x and y. So the representative of x is called x. You can call it, okay, I should have given some different name, but fine. The representative of x is called x, the representative of y is called y, okay? If x and y are same, that means both x and y belongs to same union. That means same group. Then the union is already done, nothing to do, return 0. When we return 0, when they are already in the same thing, okay? Now come to the case when they're not already in the same group. Okay. So what we'll do, whichever one has the union group means either a group will be larger than the other, okay, or see that is the case, right? If they doesn't belong to the same group, see imagine two gangs, one of them may be a larger one, okay. So this is what we're checking. Whichever is the larger gang, merge the shorter one with it, okay. Self the size of x. If the x is greater one, what we'll do? We'll make the representative of group y as x. Okay, we'll make the representative of group y as x, and this is how we are changing the sum size of it. Okay, size of x. So when we say size of x represents, see x is a leader, right? X is a representative. So under x, the group which comes under x, what is the size of the group? How many members are in that group? That is basically the self dot size of x. Okay. So we are changing the size. See, do not consider these things for now. If you're a beginner, just consider if the size of group X is bigger than the size of group Y. What we're doing is we are making the representative of group Y also as group X. Okay. In the other case, else case, that means Y is bigger than X. So what we're doing, we are making the representative of group X as Y. Okay. Now we have merged two components. Okay, we have merged two components. That's why for the total graph, we are removing the total number of components by -1. Okay, we are reducing the total number of components by -1, and we're returning 1. Try to understand what we are returning in which case. If they are already belonging to the same union, same group, we are returning 0. If we have really done a union, that means we have merged two different components, then we are returning 1. Okay. Now come to the find function. What we'll do is find function will as I have told you already in this, find function will return the representative to which x belongs. Okay. The representative of the group to which x belongs. Okay. If x is the representative of itself, then return x. If this is not the case, return the representative of its parent. That is the basic idea. Okay. Return the representative of its parent. This is like a recursive call, and ultimately it will return the root node. Okay. That's why I'm calling it returns the root node of the parent hierarchy. Right. See, my basic advice to you will be this is how it should be implemented in every case. It's kind of you will have to memorize this. Okay, this is a very well defined data structure, a well defined algorithm. You will have to memorize this part. This is how it works. Okay. Uh, See, I cannot spend more time explaining how this thing works. I understand if I think for the first time it's difficult, but for now, let us skip this part because see, you will understand it only by using it multiple times. Okay. The first time is difficult to explain you, but for now, let me quickly jump to the solution. So by now you would have understood what it means. See, to check if the individual graphs are connected, we'll see, as I have told you, whenever we are joining two components, we are reducing the total number of components by -1. And I have already told you the components initialize with n. Okay, that is the number of nodes. Each node state has a different component. So by the end of the algorithm, if we are remaining with only one component, okay, that means all the graphs are union, and finally we have out of see, we started with n, we are getting reduced to 1. That means everything is traversable. If this is not traversable, as we will see now, we return -1. Okay. That is the basic idea. Yeah, now coming to the solution part. Okay, now we'll quickly come to the solution of this question. See, whatever we discussed now was the data structure. Okay, what I'm doing, I am using a separate graph. I'm going to build a separate graph for Alice and Bob. Okay, so we are going to use this unified data structure separately for Alice and a separate one for Bob. Okay, what is n? We are passing n. Cn is going to be passed through the constructor. Okay, this is the constructor. If we initialize the parent array, that means this is going to be array size for each of those representatives, parents representative. Okay, and the components. Okay. Fine. And remove. What is remove? This is the edge which we are going to require. Okay. This is the number of edges which are going to require. Finally, what we'll do, we'll subtract from the total as given to us, we'll subtract the number of edges which are required really. So this will give me the number of edges which are not required. See, I will again repeat. We are going to subtract the number of edges given to us in the question with the number of edges which are actually required. This is the number of edges which are actually required, which are must. Okay, we cannot traverse the edge fully without them. So this is going to be the remove array. Okay, remove integer. So see, our strategy is very clear here. Okay, because type 3 is going to be common to both Alice and Bob. So what we'll do is we'll begin with type 3. Okay, this we are dealing here with type 3, and here we are dealing with type 1 and type 2 separately. Okay, so let's just first think about type 3 only. So we are traversing the edges array. Okay, this is called T, the next one is called U, and the next one is called V. Okay, so I can repeat, this is T, this is U, and this is V. Okay, so if T equal to, that means if we are talking about the type 3 edges, okay, type 3 edges are the ones which are considered for both Alice and Bob. Okay, so what we'll do is do a union of U and V. See, this edges between U and V, right? Do a union of U and V for Alice, do a union of U and V for Bob. This function you must be removing this is written either 1 or either 0. Okay, when it returns 1, see, if U and V are in the same union, that means they are already, their representative is same. Initially U and has a representative which is U, V has a representative which is V. Initially they will not be same. Only if both the representatives are same, it will be see, if the representatives are same, it will returning 0. Okay, if the representatives are not same, they will be union. That means U and V now belongs to a single group. Okay, so in this first case, A will be also 1, B will be also 1. Okay, see, the idea here is if this edge, okay, this is a single edge, right? But we are considering it in two different cases. Okay, the idea here is if you, the edge between U and V of type 3, if it is it's a must in any one of them. Okay, it's a must in either for Alice or it's a must either for Bob. This is what it's saying here. See, if it's a must for any one of them, then it make it as a mandatory one. Please try to understand what I'm doing here. See, Alice has a different traversal, Bob has a different traversal. It will also use type 3, Bob will also use type 3. Okay, so it may not be a mandatory one for Alice, but it may be a mandatory one for Bob. So if it is mandatory for any one of them, that is what is, if we are checking here, if it is mandatory for any one of them, A equal to 1 means it's mandatory for Alice, B equal to 1 means it's mandatory for Bob. If it is 1 for any one of them, count it as a mandatory edge. This is what, see, this is a count for mandatory edges which are must. Okay, make it as a count it as a mandatory edge. Okay, this was all about type 3 edges. Now come to type 1 and 2. Okay, we're again traversing the edges, and this is for type 1 now. Okay, again do a Alice union for Alice for U and V. If it is a mandatory one, add it. Okay, similarly do it for if T equal to 2. Just do a union of U and V. If it is a mandatory one, it will return 1. See, if it is a mandatory one, it will return 1. Okay, then add it to remove. See, this union will return 1 only if, see, already, see, if and U and V are already in the same union, that means if they're already connected, then the current as which we're discussing about between U and V, it is not required, right? It's not at all required. So that is what I'm saying here. This function will return 1 only if U and V were not already collected. Okay, this function will return 1 only if U and V were not already collected. Okay. So we are adding the remove array, and finally, see, we are checking here first if the number of components, and see, we started with n, right? See, this is where it is. We started with n. Okay, several components was n, but every time we are doing union, we are reducing the number of components. If at last it is 1 for Alice, that means all the nodes came for Alice as a single union, and similarly for Bob it is 1. Only then the graph is fully traversable for Alice and Bob. If it is not so, this case will come. Okay, this case will come where we have written -1. Only if the graph is fully traversable for both Alice and Bob, then only run this condition, otherwise written -1. On what is this condition? See, this length is given to us. These are the number of edges, right? Here in this case, 3 edges. So subtract the edges length is given to us. Okay, the edge is given to us from the number of edges which are mandatory. What we're doing, number of all edges possible. For example, number of all edges given to us minus number of edges which are really mandatory. So what it will give? It will give the number of edges which are not at all required. Okay, which are optional. So that is what is the answer. So yeah, friend, that was all. I understand it's a hard question, but see, as I told you, Leetcode is for last 3 days it is giving questions on this data structure. That means it's trying to show the importance of it. Okay, so we also have to take it as an important one. And let me tell, this question was on an easier side, to at least for the beginners to understand. Okay. Uh, yeah, so that was all. This question nice to, a very nice question to start with. Okay, if you're a beginner, if you have this example, if this question you have as an example, then definitely I will say it is a good one to start with. So yeah, friends, that was all for today. If you have any doubts, please do comment below. See, everything here has a meaning. That's why, see, I will post this thing in the comments also. But please go through it once, okay? You will have to go through each and every word. See, initially it will not be able, you will not be able to understand because it's written by someone else, right? But when you spend some time with it, and especially this class, okay, please copy this class in some and save it somewhere. Okay, if you are really preparing hard for interviews, I will say you should have a template of this. This is going to be really important, and you should be remembering this. Okay, otherwise you can't code it on. See at a, on the instant, on the go, you cannot code it as it is. These things should be saved as a template. Okay, and you have to refer this regularly to remember it. That was all I can say. So yeah, friends, that was all for today. Thanks a lot.